Another important term that we'll have to work with in probability is relative frequency. Now, another name for this that we will use very frequently through the course is proportions. Essentially, what proportion of our sample fits in this category? That's the idea of relative frequency. Now, what's the difference between a relative frequency and a probability? Well, probabilities look at possible outcomes, what's possible, while relative frequencies look at the results of testing this in real life. For example, what's the probability of rolling a 6? Well, we did this in the last video. There's one way to roll a 6 out of 6 different ways to roll, 6 different possible outcomes rolling a die. And so looking at what's possible, we say that there's one successful outcome out of 6 possible outcomes. All right, now I want to know if this is true. So I'm going to take a die and I'm going to roll it 10 times and I get a 6, we'll say 3 different times. So now I take this frequency or proportion and say, what proportion of my rolls were successfully a 6? Well, by proportion, I'm going to do a little p, and 3 out of my 10 rolls were 6s. And so 3 divided by 10 is 0.30, or 30% of my rolls ended up being 6s. What happened? My probability says that 16.67% of, did I say that right? 16.67% of my rolls should be 6s. But I got 30% of my rolls being 6s. What happened? Well, not too hard to explain. Essentially, probability doesn't determine real life. We could say, what are the odds of something happening? But then once things actually happen in real life, it's a different story. However, there is still a connection. Don't think that these are now different things. There is still a strong connection. Let me show you. Here I have the top is my probability distribution of rolling a die. You can see that the height of the bar is the probability of rolling any particular number. And rolling a 1, a 2, a 3, a 4, a 5, or a 6, they all have the same probability, 16.67%. Okay. Remember when we talked about distributions, we said, well, if all of the bars were about the same height, we'd call that a uniform distribution. Rolling a die is a uniform distribution. Why? Because the probability of rolling any one number is the same. That's just kind of a side note here. I just want you to see that. Okay, now on the bottom, I have the relative frequencies after 10 rolls. And I did this with a computer simulator, so the numbers are slightly different than what I had. But it looks like I rolled a 6 one time out of 10 rolls in the simulator. Okay, so 1 out of 10, that would be 10% or 0.10. That's where my 6 is right here. So what happened? Well, real life happened. There's still, even though there's only a 16.67% chance of rolling a 5, there's a chance that I could keep rolling a whole lot of 5s. I rolled 10 5s in a row, and I could get all 10 rolls would be 5s. There is that possibility. So real life happens. I don't always get a perfect scenario. But what if we rolled our die 100 times? Or we could make this easier, take 100 dice and just roll them all at once. Woohoo. Either way, it's the same idea. Let's try that. Oh, that doesn't look too bad. It looks like now the relative frequency of rolling a 6 is somewhere around 0.125, or 12.5% of my rolls were 6s. That's better. Definitely a lot better. What if I roll it 1,000 times? Oh, this time it looks like 17.75%. 0.1775 basically is what I'm seeing here. 0.1775 would be the relative frequency of rolling a 6. It's getting closer. Let's do 10,000 rolls. Oh, now we're at right around 16%. Let's do 100,000 rolls. What would happen after a million? What would happen after an infinite number? You see what's happening to these numbers. The larger our sample size is, the closer our relative frequencies get to the probability. Excuse me. Okay? Relative frequencies get closer to the probability with larger sample sizes. If you want to use the word proportions, that works too. The larger our sample size, the closer our proportion gets to the probability. This is known as the law of large numbers. As the number of trials in a probability experiment increases, then the relative frequency or the proportion of an event gets closer to the true probability of that event. With that, we can actually come back to our original definition of probability, which looks something like this. The probability of an outcome is the proportion of times the outcome would occur if we observed the random process an infinite number of times. If we could get an infinitely large sample size, then the proportion of a particular event would become the probability of that event. So that's a more official way of defining probability. If you still want to stick with it's the ratio of successful outcomes to possible outcomes, that's fine. That's true. That's 100% true. This is looking at more of the official definition of probability.